morning. My name is Andrey Egorov. I'm from Russia. I'm from Moscow Engineering Physics Institute. And also, I represent the Specialized Electronic Systems. This is a Russian company which performs radiation tests in Russia. So I would like to say that today is April Fool's Day. So I'm very pleased to make a presentation today for you. But I must also say that the audience is not affected in any way, so the audience is not the case. So the purpose of my presentation is to get you acquainted with the current state and perspectives of laser radiation hardness investigation and testing techniques in Russia. How to shift the slide?
Yeah.
So,
I think this one.
It's this one. Okay. So here you see the presentation outline. It will cover the following topics. First is classification of laser tests and techniques. Then I'll go spend some time for describing laser single event effects tests. Then I will shift to single event effects investigations. Then we will see the compendium of laser SE tests in MEPhI and SPELS during last years. And I will say a few words about the future trends in our work. To start with, I'd like to say that laser techniques are proved to be fast, convenient, and cost-effective tools for radiation hardness evaluation tests. And in Russia, these techniques are officially allowed to be used for IC radiation tests, and the particular application areas are covered by the applicable regulations. So this chart represents some classification of laser techniques that we are using now in our test center, and we will discuss them in detail in the presentation. As you know, single event effects induced by heavy ions, protons and neutrons have become a serious limitation for the reliability of electronic components. Single event transits in the IC can be simulated by focused laser radiation. You know this also. And main advantages of this approach you can see here. First of all, it's lower price than the accelerators. It is quite easy to implement, and also it allows to test individual elements of the IC, which is hardly possible with ion beams. And of course, there are also disadvantages. Laser can't pass through metal layers of the IC. It can't ionize the electric layers, and the spot size is also an issue, because we can't focus to the spot smaller than about a wavelength. So let's go through some operations which we perform usually. So the first of all is sample preparation. Pulsed laser also can be used for this task. So, So we can decapsulate the packaging of the IC. And depending on the packaging method, we can remove the metallic covers. Also, we can remove the ceramic packaging, and we can also use laser to thin the substrate in order to perform backside irradiation. So the next operation is chip identification. So after we decapsulated the IC, the chip is identified by its technological marks. So you see two chips here, they with identical marks. And if this device is in the base of previously tested ICs, the radiation laser tests are performed in several selected points, like this one. And we check the response to the laser radiation. And if the response is equal or similar, we can consider that the device's sensitivity to radiation to ions probably will be the same. So here you see a bunch of laser facilities which we use in our company. So these facilities include radon series for dose rates effect, and also Pico and Femta laser simulators, which are used for to simulate single event effects. And here you can see the schematic diagram of these facilities. So let us look through some role and place of focus laser facilities in single event effects research and testing. So the main activities include debugging and testing procedures and equipment, ion and laser, single event effect cross-section, curves correlation, testing of flip chip ICs, SE sensitive nose mapping, volt-ampere characterization of parasitic p-n-p-n structures, survival tests of ICs, performance check of SE protection systems, SE tests at different temperatures, electric modes, and so on. Here is some basics of laser simulation. So laser can produce almost all types of ICs. Can be used to test all types of ICs and can simulate almost all SE effects in them. So we can use single photon absorption when photons have enough energy to make electron hole pair, and also it is possible to use two photon absorption. And the application of the latter techniques is somewhat more complex. So because of nonlinear nature of this effect, and so we use two photon absorption only for research, not for qualification tests. Although the special distributions in these cases differ from that of real heavy ions, it is often possible to simulate similar electric effects in both cases. And that's the basis of laser simulation. So let's say a few words about pulse duration and wavelengths of laser. The situation depends on the IC response time. The shorter the response time, the shorter the laser pulse duration is needed to simulate the effect. For some advanced electronics, the typical response times may be as small as several hundred picoseconds or maybe tens picoseconds in some rare cases. So laser pulses of the same or shorter durations are needed to simulate effect in these devices. So the wavelength is also very important. So taking into account the dependence of the charge generation rate in silicon, we can say, and the typical thickness of active layers in ICs, we can say that the optimal value of wavelength is about 900 nanometers. But if we use backside irradiation, then 1064 nanometers is the best choice. So now let us focus about main approaches used for laser SE tests in Russia. And after the chip is identified, it is usually checked for presence in previously tested database. So we can then check the electrical response of this IC in some selective points if we tested it already, and if the device has same sensitivity, we state that the sensitivity is confirmed for this device. And if no, then we use the full test. For rather simple devices of micron size, like this one, focused laser technology, focused laser approach can be used to determine its sensitivity. When such devices are tested, it's relatively simple to determine the equivalent LET by measuring the threshold pulse energy. Some assumptions you see here. So the laser intensity does not change in the active layers, and the laser pulse should be very short. So in complex ICs with multiple metal layers, this can significantly complicate the application of focused laser techniques due to increased optical losses. So we have to use the next method. It consists of scanning the whole chip with focused laser beam of varying energy to determine the variable cross-section. Sometimes the optical losses in such ICs are so big that we can't measure the saturation point, saturation part of the variable curve. So we have to use the shorter wavelengths to increase laser radiation efficiency and to produce single event effects with lower energy pulses energy. And to estimate the laser energy losses and to determine the correlation between laser pulse energy and LET, in this case we use joint use of laser and heavy ion tests. So here you can see the results, example results of this technique. So we have enough experimental points on this curve to make a correlation between ion experiments and lasers. So in this way, the accuracy is of this method is quite good, but I must say that the correlation coefficient may be different for different effects in the IC because of the non-uniformity of the optical losses in the device. So we also developed so-called laser, local laser irradiation technique, which allows to estimate the SE's threshold without performing heavy ion tests. This is a very special technique, and in Russia we use it as a last resort when it is impossible to irradiate IC by ion beam. In some cases it's impossible to use ion beam, so local irradiation means laser irradiation of comparatively small IC region with variable spot size from several microns to hundreds of microns. And the spot size is varied by shifting the device away from the focus point of laser beam. This technique includes the following main procedures. The first is single event sensitive region localization by scanning whole chip. Then the determination of asymptotical value of focused laser energy. And the third one is estimation of optical losses. The following problems might arise in this technique. So the problems are here. The uncertainty of some IC technology parameters is a problem. Then significant optical losses if we irradiate from the active layer, and too much difference in the optical losses for various parts of IC. And here are possible solutions for these issues. So to estimate optical losses, we can use joint use of laser and pulsed X-ray facility. We can create the electrical response map over the whole IC crystal for further results correction. And also we can use backside irradiation. It is used when a lot of metal layers cover the active layers of IC. This approach is based on the relatively small absorption coefficient of 1/64 nanometer laser radiation in silicon. Both focused and local technique can be used from backside. For local technique, additional factor must be taken into account while determining the laser spot size, which is related to the refraction in silicon, refraction of laser beam in silicon. And to determine the depth of active layers in the substrate, several methods can be used. SE threshold energy measurements can show us the depth. Also, we can measure the electrical response timing and delay, and also we can use backside visualization with the IR camera. Also, a moderately focused laser beam, in contrary to heavy ions, can be used to localize single event sensitive points within the IC chip. As I have already said, it is done by scanning the whole chip with laser pulse with varying energy and testing the occurrence of the effect under test, like this one. So this IC has this sensitive region. And also we can use the tight synchronization of laser pulse with timing diagram of the IC to test the radiation hardness parameters at various moments of timing diagram. So there are some supplementary applications of laser techniques. So one of them is the SE Perry technique. Here laser allows us to reveal the critical modes of operation and to develop and improve these techniques selectively for different regions of IC and to develop the Perry methods of single wet light chap, for example. So we can also perform. Oh? 2 minutes. Okay. Okay. I have to be hurry. So we use cell survivability tests to initiate light chap and to know how long the IC can stay in light chap state. So this is another experiment which shows us the influence of TID. It is also made by laser, and we see here that the light chap threshold depends on the total absorbed dose and also the SET waveform also changes. So here is the compendium of laser tests in MEPhI and SPELS. So we can see that significant part, about 13% of all tests are made with the help of laser, and this part is growing, and this part is tests with laser only. So this is about 10% of all tests in our company. So these are future trends. I will not say them all. You can see here maybe. So the most important is the spot size and the two-photon absorption. So, and as a conclusion, I must say that laser techniques are developed and widely used in our company for radiation effect simulation. The techniques are officially allowed for tests, and noticeable part of tests were made with laser. And I think that's it. Thank you for your attention.